Swayam Prabha. Digital India. Educated India.
I welcome you to this lecture of flow through porous media where we are discussing about deformable porous medium. So, in this lecture we are talking about varying porosity and concept of stress and pore pressure occurring together inside a porous medium. And so, we have deformation on one hand because of compressive stress and the flow of fluid because of gradient in pore pressure. So, what we discussed before is that we can bring in a solid constituent, we can bring in a solid, we can have a conservation of mass for the solid constituent, and this is given by this expression. We have shown that U is the solid volume fraction, which is essentially 1 minus phi, and V s is the velocity of the solid constituent. So, this is given here. So, in the same token, one can draw a conservation of mass of the liquid constituent. That means, we can draw a differential element once again and write the fluid that is going in x direction, let us say, and leaving the. So, this is at x, this is at x, and this is x plus delta x. So, how much of fluid is going in? So, that is equal to V L, or let me see, V L at x and V L into 1 minus U, V L into 1 minus U into V L basically at x, basically 1 minus U into A. Why we are doing it? Because this time the liquid velocity is V L, but if you multiply this directly with the A, then as if it is just a flow without through a pipe, not with the porous medium. So, one has to bring in 1 minus U, which is basically the phi, the void fraction. So, total area is not available for flow, only A into phi, that part is available for flow. So, that available cross sectional area multiplied by the velocity, this gives me the volumetric flow rate over duration delta t, and the same thing happens here, A into 1 minus U into V L at x plus delta x into delta t, that would be the volume of liquid that has come out from the other side. And if we look at the accumulation inside, that accumulation would be once again the total area is A, total volume is A delta x. Out of that, phi into A delta x is the volume that is occupied by the fluid. So, if any change happens over this, so we will write this as change in 1 minus U, right. So, 1 minus U is the porosity, 1 minus U is the solid volume fraction. So, any change in this, so this would be written as delta of 1 minus U into A delta x. So, that is the change in liquid volume inside this the differential element, and when you equate this delta t once again goes there, and this makes it minus del U del t. This makes it minus del U del t, and on this side this makes you, this delta x goes to the right hand side, this minus this, in minus out, limit delta x tending to 0, A and A will cancel out everywhere. So, here on this side you will have this term del x of 1 minus U into V L, if we are talking about one dimensional problem. So, 1 minus U into V L with a minus sign on this side, and this side it is again del T of 1 minus u. So, this is once again is equal to minus of del u del t. So, when you take this del u del t to the right hand side, you get del u del t minus, because this both sides are minus. So, if you bring both to one side, then one has to be the minus sign, and one has to have that minus sign. So, minus of this quantity. So, this is the expression for the conservation of mass of the liquid constituent. Here the VL is the velocity of the liquid constituent, and solid and liquid densities are assumed constant. So, now instead of, so earlier we had worked with this kind of a form. Obviously, del phi del t we never considered, even for interception of solid also we assumed phi to be constant, porosity is constant. But this time we are assuming the porosity is varying with time. So, this term is coming here. So, we have now two equations, and one is for the solid, another is for the fluid, and we have the porosity term which is varying, because u is the solid volume fraction, which is simply 1 minus phi. So, with this in mind, with this in background, next what we do is we need to come up with this momentum balance for the mixture as a whole, because we have to relate this P and sigma that remains. Okay. So, P and sigma that remains, and once we have P, then we can talk about Darcy's law, because that has to follow, even if you have deformed, but as long as you can find out what is P and what is the length over which the flow will take place, then it will simply, it will be Darcy's law. So, momentum balance for the mixture as a whole, you can write this in general term as grad, basically this is del p del x plus del sigma del x. I mean that kind of term here. In general term, you write here P is the pore liquid pressure, I is the identity matrix, and Tm, because P is a column matrix, and this Tm prime is the excess stress. So, this is a tensor. So, these, so if you, when you club them together, you have to multiply this P with the identity matrix. So, counted as positive in compression, Tm prime is considered excess stress, and so this is the way it is written. Okay. This is the momentum balance for the mixture as a whole. And secondly, there is another equation which is important in this context, which is known as Darcy's law. Darcy's law is, now mind it, here this is, first of all, this is a this is not superficial velocity, this is interstitial velocity, right. So, here when we talked about this one, these VL and VS and VL, these are obviously interstitial velocity, okay, because we have multiplied this VL, we have not used the total area, we have used the only the area over which this solid fraction is occupying out of the total area. So, that means we are talking about interstitial velocity, I mean for the solid, and for the liquid the out of fraction of total area that is occupied by the liquid. So, we are talking about the interstitial area. So, since we are talking about interstitial area, so that is why we have to divide it by the phi term, k by mu grad of P, and so k by mu grad of P gives me superficial velocity, I know as per Darcy's law. But then you have to divide it by the porosity if you want to convert this superficial velocity to interstitial velocity. So, VL is the interstitial velocity. Second thing is that VL, absolute value of VL does not make sense here, VL with respect to VS. So, what is the relative velocity of liquid with respect to solid velocity? That has to be given by Darcy's law, not VL alone, okay, because the porous medium itself is changing. So, that is why VL minus Vs is written as this quantity, and this permeability K here is a function of F. It is not K multiplied by F, but K as a function of F, where F is the deformation gradient. Deformation gradient means deformation gradient relative to the solid constituent, and so K is a function of F. So, this deformation gradient F is, can be written as del small x del capital X. So, we have a system here small x which are based on the actual coordinate and capital X which are the coordinates in reference configuration. What that means is that suppose I have this as the porous medium. So, we will have the, let us say this is the porous medium and this is, and we have defined x and y with respect to the fixed coordinate. So, this is x, this is y, and let us say this whole thing is changing now, and so this whole thing is giving compressed in this direction. So, then this becomes the coordinate here, this becomes the new coordinate, because porous medium which was originally this much, this is the porous medium. Now, this is the porous medium. So, this is being compressed by up to this level. So, one is you can continue to have this fixed coordinate system. Another is if you look at the edge of this porous medium, then you can call this as the coordinate system. So, we call this coordinate system, this original with reference to what's fixed reference, which we call it in the reference configuration. So, this is called capital X y, and this which is moving with the porous medium we can call this small x and y. Okay. So, now this f which is the deformation gradient is del small x I, in I is the ith direction 1, 2, 3, that I, j, k, there are 3 different dimensions, del capital X. So, del x I del small x del capital X, that is known as the deformation gradient with relative to the solid constituent, and it is assumed that this permeability depends on this f depends on this f influences the permeability. Okay. Obviously, more deformation, that means permeability would change. Okay. So, here the permeability is also not constant, porosity is not constant, that that we have already discussed, that the porosity that or in other words the solid volume fraction is going to change with time. So, that is why we have that term del u del t. So, the porosity is going to change and permeability is related to this deformation gradient, where deformation gradient is defined by this quantity, and mu is the viscosity of liquid. If we try to look at these as the situation in one dimension, if we look at this situation, before we go to the one dimension problem in one dimension, I must point out at this time that one can define a composite velocity. Composite velocity is that you have multiplied this V s, which is the interstitial velocity of the solid, multiplied by the solid volume fraction, interstitial velocity of the liquid multiplied by the liquid volume fraction. So, these are basically weighted velocity, and weighting is done by the corresponding volume fractions. We have done this in case of suspended solids in the beginning lecture of interception of suspended solids. There we discussed about this kind of weighting and finding a composite velocity. Here also we can come up with a composite velocity. So, one can say that the entire porous medium, solid and fluid, they are having a composite, a single velocity, which is V c, where V c is the composite velocity, which is basically the average of solid and liquid weighted by their corresponding volume fractions. So, then you can note here that the mass conservation equation that we have talked about in case of solid, this was the equation, and this is the mass conservation equation we discussed just now for the liquid. We had 2 equations, right, one for the solid and the other for the liquid. So, in this case we can see that this del u del t is this plus the change in flow in minus flow out as far as the solid volume fraction is concerned, and the other thing. So, now if we subtract one from the other, so subtract means this becomes minus and this will cancel out, this minus becomes plus and it is 0 only. So, then this becomes, you can see one can write this as this quantity is equal to 0, which is essentially the continuity. So, continuity equation applies to the composite velocity. So, I can note here that the way the fluid velocity we have considered and the mass continuity for the fluid we considered, in this case we have a mass continuity of the solid, mass continuity mass conservation equation, but we are not, since the rho for the solid and fluid they are considered constant. So, it is automatically the volume conservation. So, this is for the solid is there, for the liquid this is there, and if we subtract one from the other, we see that the continuity equation that we have seen, in case of flow through porous media, that was for superficial velocity. That continuity equation we can apply if we consider the composite velocity. That means the corresponding solid and liquid velocity weighted by their corresponding fractions. So, this equation, continuity equation, applies here, and this has a very important implication in the sense, if we are talking about a one dimensional problem, that means this solid and fluid they are getting compressed, then for a one dimensional problem this becomes Vc is equal to 0, Vc is equal to constant. So, Vc becomes invariant over the space. Okay. So, that means the composite velocity, if you are looking at a one dimensional problem, that means this is coming down. So, after some time this becomes the volume, this becomes the porous medium. So, this much is compressed. So, in this case, in this problem, you can assume this entire process is happening with this composite velocity same everywhere, every point on this porous medium. Okay. So, that is how that. So, at any time, say let us say now this is the porous medium, you can assume that the composite velocity at every location is constant. So, with this idea we can now look at, we had talked about this conservation equation and we had talked about this momentum balance and Darcy's law. If we look at simple one dimensional form, because that is easier to handle, that is easier to deal with. So, in one dimensional form we have, instead of this term del u del t plus this in minus out for the solid component, we have or rather we focus on the liquid part. So, for the liquid part, this equation in one dimensional form can be written as del u del t is equal to, or del u del t minus this quantity del x. So, x is the only one dimension we have, that means this was the porous medium and this is getting compressed. So, this is the x direction. So, this is getting compressed. So, earlier it was this much and then the porous media is getting compressed and flow is taking place out because there is a strainer and the solid particles are not allowed to leave the system. So, this is so in that case del x of 1 minus u into VL. This is only the liquid part of the mass conservation, which since density is constant we are talking about the volume conservation. So, this is how it is. And on the other side is del Vc del x, we said that this Vc would be constant, the composite velocity we just now mentioned. So, if we have this and this, it is equivalent to having this liquid and solid equation separately. Either we can use this and the solid, or we leave out the solid altogether, we focus only on the liquid and we use the continuity in the composite velocity. So, the specification becomes complete. So, either way you need two equations, one for solid, one for the liquid, or one for the liquid and one for the composite. So, bottom line is the same thing. And then when it comes to the Darcy's law, once again these are interstitial velocity. So, that is why we have the porosity term phi coming in the denominator, otherwise minus k by mu del p del x. This is the standard form of Darcy's law, and we have to subtract this velocity of the solid, because the liquid is, now we are looking at relative velocity of the liquid with reference to solid. Earlier this Vs was 0 in case of a fixed porous medium, but since it is deformable, solid itself has a velocity. So, basically the flow is occurring as a relative velocity between the liquid and the solid. So, or in other words, the pore pressure that is, or gradient in pore pressure that is existing and that is instrumental in having a flow, that is because that is causing this relative velocity. Anyway, the fluid will move because there is this solid is moving. So, but over and above the velocity of the solid, the liquid is moving. This additional movement is arising because of the gradient in pore pressure. So, that is what that is how it is related in Darcy's law. And the momentum balance equation that we had earlier, this equation is in one dimensional form. It took the shape of this del sigma del x plus del p del x is equal to 0. So, in this case VL and Vs are the interstitial velocity in x direction, that is, it is only a one dimension we are talking about. K is called K originally in a general notation. K is a permeability tensor, okay. But out of these, basically if you take the permeability tensor, you have Kxx, Kyy, Kzz, and then you have other cross terms there. Okay, so these are so we are talking, since we are talking about only one dimension, problem is one dimensional. So, we are talking about Kxx term of the permeability tensor, or in other words, we have the, in one dimensional system we have a permeability that is the same. So, this basically from the general we are coming back to the to a single value of permeability, and sigma is this Tm prime, that was the excess stress tensor. Basically, if we have a differential element, then we can subject this differential element to, I mean, we can say that this is, we are, or we can consider a stress tensor at a particular point. Let us say we have x, y and z direction, then there would be, if this is x, this is y and this is z, let us say. So, then this would be sigma xx would be acting in this direction, or we can call this one second, we can call this Tm prime xx, in this direction also Tm prime xx, then we will have Tm prime yy, Tm prime yy, Tm prime zz, Tm prime zz, and then there would be cross terms, which are basically the shear stresses. That means, you have Tm prime xy, Tm prime xy in this direction tangentially, Tm prime yx, Tm prime xz, zx, like this. So, basically you will construct, if you look at all the stresses that are acting at this point, a differential element around that point, you will find that one can write Tm prime xx, Tm prime yy, Tm prime zz, and then you will have cross terms here in this tensor. So, generally if it is a static system, or if it is a static system, you can have these pressure is defined as the minus of average of these three diagonal elements. Okay. Now, since this is a one dimensional system, so you can have not necessarily a static system. I mean, pressure is defined as the This average of these three diagonal elements, this is called bulk stress, and minus of that average, minus of this average bulk stress is called pressure. So, here in this case, in this particular problem, sigma would be, but this is true for a fluid flow problem, but in this case it is in this case the sigma is equal to T m prime xx value of the excess stress tensor, because this is here we are looking at the excess stress. Okay. So, that is why this element is basically the x value. So, anyway, this is just from general one to one dimensional problem, but the fact remains that we have this equation we can satisfy. This equation needs to be satisfied. So, sigma and p, they are related by this VL minus Vs, this is the relative velocity of the liquid, which is given by Darcy's law, and you have to have the volume or mass conservation, which is essentially volume conservation, since rho L and rho S, they are constant. So, either you use the liquid and solid conservation equation, or here we have used liquid and the composite conservation. So, one and the same thing. So, these are the four equations which are the four pillars here in this deformable porous medium, and these four equations need to be understood. These four equations need to be solved, need to be recognized, need to be solved simultaneously. So, what we will do in the next class is, now first of all we have this permeability. This permeability term, we said permeability was a function of f, the deformation gradient. Okay. So, now this permeability is one term, and the other term which we are concerned with is the sigma. Okay. So, we need to find out how these terms are going to change. In particular, we are going to talk about next. What we are going to talk about is our approach would be that we will define sigma and k. These are function of f. Okay. Sigma is that excess stress and k is the permeability, and we have to somehow consider this sigma as a function of solid volume fraction and permeability as solid volume fraction, and we will use some constitutive equations. These are the constitutive equations which are commonly used for this type of problem, where in terms of the solid volume fraction, and solid volume fraction means it is essentially porosity. You use essentially in complementary to porosity. So, that is how. So, basically these are, you can say that permeability and sigma, they are dependent on porosity, and how they are dependent, we use some constitutive equation where these constants gamma, alpha, delta, beta, these constants are to be determined. These are experimentally determined parameters. So, once we know this, we know how sigma, if u is changed, solid volume fraction is changed, how the permeability is going to change and how that excess stress is going to change. So, this relationship would be should be at our disposal, and once we have that, we can then talk about these, then we can solve these equations with that information to get to the final, we have to specify the problem of deformable porous medium fully. So, then I will be able to specify the problem fully. So, that is all I have as far as this particular lecture module is concerned. I will continue this lecture. There are other concerns as well, that probably you have some little bit of idea about the small x and capital X. Okay. So, one has to consider something called a Lagrangian formalism, because whatever is your x, that x is continuously changing, because porous medium itself is getting compressed. So, how to handle this? So, this is also another major step in this regard. So, this is something which we will discuss in the next lecture and complete the specification of deformable porous medium. And what we and also it is important what we expect, how the porosity is going to change. Okay. So, I mean we have already related porosity with the compressive strain, but if we talk about the stress, if the stress is imposed, then how the porosity is going to change, at least some trends we need to look at. So, that is something which we are going to discuss in the next lecture. That is all I have for this particular lecture module. Thank you very much.